If sustaining a high metabolic rate lifestyle depends upon the ability to capture large amounts of energy, how practically does that work? Well, it works the old-fashioned way. You capture more energy by going out and finding it, and for animals, this means moving around looking for it. Let's start by looking at the energetics of locomotion, moving around. We can take an animal, put it on a treadmill, and make it walk, run, or gallop at ever-increasing speeds. If we measure the animal's rate of oxygen consumption as it's running, we'll get a curve that looks something like this. As the animal runs faster and faster, the oxygen consumption rate will increase up to some value where it will begin to level off. At running speeds faster than this, the oxygen consumption rate will not increase any further, establishing a maximum oxygen consumption rate, which we will call V.O2 max. If we compare this to the resting metabolic rate, the V.O2 max is quite a bit higher. There are a couple of interesting and curious features about this. For example, there can be no such thing as a running speed of 0, but if we extrapolate our running oxygen consumption curve down to 0 running speed, we will find that there's a slight gap between resting oxygen consumption and this extrapolated minimum value. No one knows why this is. I just offer it as a curious phenomenon. The fact that oxygen consumption increases linearly with running speed over some range allows us to begin to calculate some interesting energetic properties of locomotion. For example, we can calculate a slope of this curve, which we can name as something called the aerobic cost of transport. This has units of moles of oxygen per meter, which is just the ratio of the units of the y-axis, moles of O2 per second, over the running speed in meters per second. The aerobic cost of transport corresponds to the consumption of oxygen that is correlated with moving the body over a distance of 1 meter. We'll have occasion to go more deeply into this quantity a little bit later, but for now we want to pay attention to another value. If we measure the span between the maximum oxygen consumption, V.O2 max, and the resting oxygen consumption, let's call that V.O2 rest, we get a quantity known as the aerobic scope. Now, we can define aerobic scope in one of two ways, both of which will be important for the argument we'll be developing. We could, for example, calculate the aerobic scope as the difference between the maximum oxygen consumption and the resting oxygen consumption. That will give us a number with units of moles of oxygen consumed per second. We can also define the aerobic scope as the ratio of the maximum oxygen consumption rate over the resting oxygen consumption rate. This value would be dimensionless because the units in the numerator and denominator are both the same. This quantity is sometimes known as the aerobic capacity or aerobic expansibility. No matter what we call them, though, each of these terms tells us something slightly different. Let's shift gears now for a moment and recast this in terms of energetics. Here's our plot again with our curve of oxygen consumption versus running speed, with its linear increase over a certain range of running speeds, and with the leveling out of oxygen consumption at some maximum value. But let's reflect on what this means in terms of the energy cost of transport. The reason that oxygen consumption increases linearly over a certain range of running speeds is because oxygen consumption is tied intimately to metabolic rate, which we must constantly remind ourselves is an expression of energy consumption. So what we're really plotting here is metabolic rate in watts, that is joules per second, against running speed. Now, why should the metabolic cost of transport increase linearly with running speed? Well, it's a simple matter of Newton's laws. The forward motion of the body is a momentum, and work has to be done to sustain that momentum. Momentum is the simple product of mass times velocity. Therefore, you would expect the work done to impart forward momentum to the body, that is, to running, to be linearly related to running velocity. This physical requirement applies no matter how fast the animal is running. Therefore, we should be able to extend the curve of metabolic rate versus running speed indefinitely to ever higher and higher values. And we would expect a linear relationship to apply everywhere along this curve. Thus, we should be able to calculate an energy cost of transport in joules per meter that's equivalent to the aerobic cost of transport in moles of oxygen consumed per meter. But we can see that the two curves don't match over the entire range of running speeds. At lower running speeds, the match is pretty good, but at higher running speeds, as oxygen consumption levels off, the departure between the energy cost of transport and the oxygen consumption to support it increases. This quantity is known as an aerobic deficit, and the accrual of an aerobic deficit leads to something called an oxygen debt. What's actually going on here is that the animal is still incurring an energy cost to move its body forward at higher and higher running velocities. It's just not meeting that cost through aerobic metabolism. The energy still has to come from somewhere, though, and where it comes from, of course, is anaerobic metabolism. We'll have a bit more to say about this in a later lecture. For now, though, I want to make a point. There are two phases of locomotion: a lower range, where locomotion is powered by aerobic metabolism, and a higher range, where it's powered by anaerobic metabolism. This means that for any animal, there's going to be a maximum aerobic running speed, and this is going to be determined by the aerobic scope. So, why does this maximum oxygen consumption limit even exist? Why is there an aerobic scope? Let's take a look at the process of delivering oxygen to the mitochondria. We start with a cell with a mitochondrion living inside. Getting oxygen to the mitochondrion involves a sequence of physiological steps that we've already talked about in some detail. Oxygen comes into the lungs, is transferred to the blood, and is pumped by the heart out to the capillaries, where the oxygen diffuses into the cell. The blood is then returned back to the lungs to start another cycle. Each of these stages has a particular range of capabilities. If we look at the capacity of the lungs to support oxygen exchange, for example, there is a range ranging from a minimum value up to some maximum value. This variation is supported by variations of breathing rate, depth of breathing, and those sorts of things. Thus, we can say that there is a kind of pulmonary scope, similar to what we've described as an aerobic scope. We can say the same thing about the circulatory stage. The circulatory system can transport oxygen at a range of rates, ranging from a resting value up to some maximum value. The variation there comes from variation of heart rate, stroke volume, and those sorts of things that we've already discussed. But just as we could for the lungs, we can say that there is such a thing as a cardiac scope. Now, there are a number of interesting things we can say about this. One of the interesting things is that the two scopes should co-evolve. Because these are two transport processes that operate in series, it makes very little sense to have a very large pulmonary scope, for example, without having a cardiac scope that can vary with sufficient range to match the lung's own scope. So the pulmonary and cardiac scopes should always roughly match one another. This is a phenomenon known as Symmorphosis. Another interesting thing we can say is that these scopes for exchange capacity are what set the aerobic scope. We've already seen in comparing energy wastrels and energy misers that the principal difference between them is in the mitochondrial densities and in their metabolic capacities. The more mitochondria and surface area within mitochondria to support oxidative metabolism, the higher the potential oxidative metabolism will be. How high that metabolism can actually get will depend upon the capabilities of the supporting infrastructure, so to speak, namely the lungs and circulatory system to deliver oxygen to them. So, the limitations of the aerobic scope apply equally to both energy wastrels and energy misers. This fact is going to help us understand something about the selective forces that underlie the divergent selection that has led to the current stark division between the two metabolic lifestyles.